recording. Okay, so we are starting with chapter 4 today. We'll get as far as we can. I realize I don't have a lot of questions for today. So if we do get all the way through, I'll try to see if I have some questions. If I don't have any today, I'll try to see if we can have some practice questions for Thursday. Okay. So with this chapter here, I'm going to have this. So feel free at any point to ask questions. And I know y'all talk a little more than my other class. They're very quiet people. But this chapter talks about gases. So it's an introduction to the chapter about gases. It does start off from where we left off in chapter 2. So the objectives are listed right here. I will not go through the objectives. Feel free to go through. But when you're done, you should be able to accomplish these objectives. My goal is to actually get through the details so that we can actually have more practice, you know. But if you want to know what we are covering, all the objectives are listed in the beginning of the chapter. I did take the ones for chapter 2 out, but I'll try to see if I can find them and then put them back in. But these are pretty much it right here. Okay, so yeah, I'm gonna skip over all the fluff stuff and get right into the meat of things. When it comes to gases, we're talking about the characteristic of gases. We discussed this in chapter 2, where we talked about the behavior that we see that the gas molecules have, which is because of how far apart the gas molecules or the atoms are compared to each other, gases may actually be compressed, right? And when you're compressing the gases, you're applying an external pressure to push the gas molecules closer to each other. Compressing gases will take them from a gas state to a liquid state if they're very compressed. So compressed gases become liquids if the external pressure, if the pressure applied is very high. Is very high. Make sure you're taking notes so that you know, and if you miss anything, feel free to come and watch this later on. You can review it and then you can take the notes if you miss something, right? For that reason, gases may be compressed and they may also be expanded. Remember the intermolecular force we mentioned earlier, the force of attraction between the particles was very minimum. For that reason, these gas molecules have the greatest freedom. They're able to freely move around and have a very high velocity. So these gases can also be expanded. You can apply a high temperature or reduce the external pressure to allow the gas molecules to travel around even freer. Or you can change the container's volume. So if you want to expand the gas, you can do so by increasing temperature, decreasing pressure, or by increasing volume. So if you increase the volume of the container, that allows for more room for these gas molecules to expand too. When we say they're expanding, we don't mean the size of the atom is getting bigger. We just mean that the molecules are traveling to occupy the new available space. Because of all the interatomic distance, all this empty space right here in between, gases do have low densities. And we're told here, gases may be mixed in a fixed volume. You can have one gas mixed with the other to make a solution of gases. And then we're told here, gases exert a constant pressure on the walls of their container uniformly in all directions. So I want to talk about the pressure of the gas. And before I get into that, I want to give a backstory about me in my younger days. I used to be in track, and one of the trainings that we did in track, especially if it was really cold outside, this was happening in Kansas, was we were inside the gym. Not actually the gym, it was a basketball court. We were inside, and the coach would have us run drills, and he would have us run from wall to wall. And the idea was you run from one end of the room to the other, and as soon as you got to the wall, you tap the wall, turn around, and run to the other end. And we kept doing that over and over, so many reps. And then when we're done, we'll take a break. He'll say stop and then get at it again. And I'm assuming we're supposed to increase our strength or our speed or something. I had no idea. I mean, he was trying to get us better, and that's all I knew. So we were running from wall to wall, and each time it was important for us to tap the wall when we got to the wall, turn around, do the same thing over and over again. Now you had those people who were very fast, and you just heard tap, 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 tap. We didn't all get to the wall at the same time. We all had different speeds. The slower ones, yours truly, got to the wall eventually, tap, turn around, went around, back to the wall. And all of us did not have the same speed, so you heard us, tap the wall at different times. So imagine us being gas molecules, right? And so the gas molecules do a very similar thing. Each molecule has its own speed, and they're traveling in straight line going from wall to wall. So let me go ahead and erase this a little bit. It's hard to erase this right here, but you have these gas molecules traveling inside the container. So I'll make the container a square, and it's going from wall to wall. So the pressure we get from gases occurs in the instant the molecule hits the wall. It's very important for the molecule to hit the wall for that pressure to be generated. So it bounces, it hits the wall, and then bounces off, and it goes off to a different direction. Then it hits the other side of the wall and goes off to a different direction. Pressure in a gas is generated when the gas molecule hits the wall. So without even reading the other PowerPoint slides, imagine if that contact right there and the force by which the molecule hits the wall determines the amount of pressure. Of course, if you have a greater force, you have greater pressure. If you have less force, you have less pressure, right? So for those athletes who were able to run to the wall, get there really fast and tap really hard and turn around, they were generating a greater pressure on the wall of the gym, right? Versus me, I'll get there eventually and then I'll just gently tap. I'm so tired, breathing hard, then I turn around. So different molecules, different amount of pressure, but the overall pressure we get from the gas is generated by the number of molecules, right? So you can see from here then a relationship that exists. If you have more gas particles, what you will observe is a greater pressure because the chances of the wall being hit is higher, right? And if the gas molecules are traveling at a very fast speed, they're going to hit that wall with a greater force because they're moving really fast. And with the molecules, unlike the people who had the intent to turn around, the molecules are actually being stopped by the wall of the container and they're being forced to leave and head the other direction. So imagine that impact. The other thing you can think about is is it racquetball? When people are hitting the racquetball against the wall, that sound you hear, each time the racquetball hits the wall, the sound you're hearing as the ball bounces against the wall to the person, that's how the pressure is generated in that point of contact, right? So the more you hit the wall, the more pressure is generated. So if you have more gas particles, you have greater pressure. Okay? So we'll get into all those details. I don't want to tell everything in that first slide. Okay, so we're talking about a property of gas. Gas can be compressed and expanded, right? So we're looking at this picture here. Remember we had that macroscopic level. This is the level where you can observe matter with your naked eye. Whatever you can see in the lab, in the world, outside of the lab, that is the macroscopic level. Whatever you can see with the naked eye, including if you had glasses on. So we're seeing this picture here and trying to see what we're watching. I guess it's labeled, okay, A, B, and then we have C, D. So from A to B, you can see from A to B, the weights here, these are weights being applied on this piston. Let me tell my friend, I'll call her later. Okay, as the weight increases from A to B, you can see here they have increased the pressure, the external pressure. But what does the increasing the external pressure do to what's happening inside? Because for the most part, what we care about is what's happening inside the container. This region right here, from here to here to here to here. When you increase the external pressure going from A to B, do you see that the same amount of gas now occupies less space? By increasing the pressure, now the volume of the container has decreased, so the gas here occupies less space. Okay, and on this side here, C and D, they've done the opposite from A, right? If you look at it from A to C, from here to here, they have decreased the amount of weight. So this would be the same as decreasing the pressure. In doing so, now the gas molecules can expand. So from A to B, you were compressing this, compressing the gas. From A to C, you're actually expanding the gas, and you do so by decreasing the external pressure. Now the gas has got more room to travel, but that means the pressure here, the pressure inside the container is decreased, right? Because think about the analogy I'm telling you of us running to the wall. If you're the one running to the wall, you will know the difference. If we went to a bigger room, it would have taken me an even longer time to get to that wall because the room is bigger. I have a longer distance to travel, right? So in this case here, ultimately the pressure will be less because the room has been made bigger. The room where the gas molecules are going to be in is now bigger. They have to travel longer to get to the wall, right? So you increase external pressure, that causes the gas to compress. Decrease external pressure causes a less pressure in the container, and the gases can expand, occupying more space. And expanding means they're just occupying more space. It doesn't mean the gas molecules are getting bigger. They're just spreading around more because they have more space. They show this to you at the particulate level. This is what it looks like. In A, you have 5 gas molecules or particles. They're very close. They're kind of close to each other, not super close. In B, they're a lot closer, right? Because the pressure, you have less volume for the molecules. They have less space to travel to. In C, the spaces between the gases is even much larger, so they're not very close to each other. In D, it's even worse, right? As the space around the molecules increase, the gases just expand to take charge or spread around all the available spaces because that's what gases do. Gases expand to fill all the available space. Unlike liquids, liquids are not able to do that. In order to get a liquid to fill all the available space, you have to really work at it. But with gases, there's no problem. It will just expand. It will spread around to fill all the available space. Do you all have questions about this? Okay, feel free. If you feel shy about talking for whatever reason, just go ahead and text it, your question right here. I have the messenger part open. Let's see, just in case. And then I'll be able to see it from where I am. Okay, so continuing on. We said yes, gases tend to have lower density because they have more space between them. So we have a particulate level here. So you have the macro level, right? Macro level is the level that you can see with the naked eye. In the lab, we will see the picture, the actual picture, not the little diagrams in the circle. You will have some gas trapped in the balloon. This would be our gas that's trapped in here. The balloon is suspended on the liquid. This is our liquid here. At the bottom of the liquid, you have a nail, and this would be our solid. This is showing you 3 different phases of matter. I'll call this gas here. It may be hard to see. We have gas, we have liquid, we have solid. And all they're trying to show us here is the relative density, right? Gases are very light. They're not very dense because there's a lot of space between the molecules. You can see the picture here. And this picture here is showing you the particulate level. Remember, particulate means the level of particulate level of atoms and molecules. Every time they mention atoms and molecules, they mean that level, particulate level. And you can see it in the pictures. The gases have a lot of space between them. Over here, the liquids are not as organized as solids. There's a lot more space than solids, but a lot less space than gases, right? These tend to be intermediate in the space, right, between the atoms, space between atoms, and therefore it also has an intermediate density. Intermediate means kind of like in between two, right? So intermediate in the space between atoms, and of course intermediate density. Gas particles, here you have least density and then greatest space. Space between atoms. Okay, so just little things that you want to be aware of as we're going through this. And of course, with the solids, the solid atoms look almost deliberate. They're very organized here. These are organized, right? They're also very tightly packed. And you have almost no space between atoms, making these the most dense. Okay, so based on what we're seeing here, this is the general relationship as far as density is concerned between gases, liquids, and solid. The expectation is gases will be less dense. They will float on liquids. Liquid will float on solids, or the solid will sink inside of the liquid due to its density. And then here we're looking at mixing gases. So we're told it is possible to add more gas to a container already holding a gas. And we can see that just because the particles here will occupy and fill all the available space doesn't mean they need it. So you're able to add more gas molecules in there, and they will mix perfectly. And then together, the mixture will expand or spread out to occupy the whole available container. Okay, so we're moving on talking about gases exerting pressure in the container, right? And so we're told here, pressure in gases and in liquids. Gas pressures are exerted uniformly in all directions, right? Because these molecules are not unidirectional. They're just traveling randomly, but in straight lines. And then they travel until they hit the wall of the container, turn around, come all the way back, and they're doing this as long as they have energy. And at some level, we'll be told that when they collide, they don't lose energy. So you can almost say gas molecules have forever energy, and until they run out, they will keep colliding and traveling and colliding with the wall forever. Okay? For that reason, they're just traveling randomly throughout the space. Liquid pressures depend on the depth of the liquid. So at some level, the pressure of the liquid is not as uniform as the gas. When you're thinking about the ocean, I have been in something that I call a submarine. It wasn't like a real submarine that went all the way in the bottom of the ocean, but it was one that went, let's say like 20 feet below. We couldn't get the other one because we went on a cruise and we were too slow. So it's more like I was cheap. Anyway, so we went on this submarine, went down 25 feet, and it was really cool. But when you're in the bottom of the ocean, right, and you're not really swimming, but I heard from those who actually swim, you feel that pressure of the water, and the pressure changes as you go further and further down in the water. Gas is not like that. The pressure you feel on the top level of the gas in a container is the same pressure you will feel on the bottom. Liquids are different. The further down you go in the liquid, the more pressure you feel. So that's what this slide is saying right here, just FYI. Okay. Okay, now we're going to be talking about the behavior of gases. We have been doing that, but we are doing this now in a more organized fashion underneath the kinetic molecular theory postulates. So these are the gas behaviors summarized by scientists based on their findings. So they're working with gases, they're realizing certain behaviors, certain repeating behaviors. They summarize the experiences, and it's listed under kinetic molecular theory. Okay? Kinetic molecular theory, like the name suggests, kinetics is motion. So we have moving, something is moving. And what is moving? Molecules or molecular. The molecules are moving here. Either molecules or atoms, either one applies. And so it's a theory of moving molecules, kinetic molecular theory. And as we look at that theory, we're studying the characteristics of gases. Okay? So the first postulate or the first idea they have in the theory is a gas consists of molecules. So if you look at the fundamental level of a gas, any gas we have, the gas we have around us that we can't see, but we know it's there, it is made up of molecules and empty space. So you have the gas particles, it can be molecules or atoms, and the rest of it is just empty space. And then we're told the volume occupied by the molecules in a gas is negligible when compared to the volume of the space they occupy. So what they mean here is, if you were looking at a container, okay, let me use the red, and your container, say, had 5 molecules of a gas, 1, 2, 3, 4, 5. And you were to take all the molecules and squish them together because you're trying to figure out how much space the molecules are actually occupying when they're in the gas or in the container. These molecules, now mind you, we're drawing them big so we can see them, but in reality, the molecules are so tiny, they will be like a dot. So 1, 2, 3, 4, 5. Imagine that this is where my 5 molecules are. And they're telling you, compare the space occupied by all the molecules in the container versus the actual space available. So scientists conclude they're not really occupying a lot of space. And the way they write it is like this. The volume occupied by the molecules in a gas is negligible, meaning we can almost neglect it because it's so small. When you compare this with the volume of space they occupy, the actual volume of the gas molecules is so small compared to all the space that's available to them and all the space they will spread out to occupy. Or some people call this whole part here the volume of the container. So I want to go ahead and paraphrase that so I can make sure that this part is not confusing, because sometimes when you're reading some chemistry authors, the way stuff is communicated is confusing, right? So what they're trying to say here with this statement is volume of gas molecules is very small compared to volume of container. So how small is it? It's so small that sometimes there's some scientists who are a little bit extreme. They will go ahead and say gas molecules do not occupy any space, right? Because it's so small compared to the space they actually spread out to occupy. Or they say that gas molecules do not have any volume compared to the volume they're actually trying to fill. But just recognize that, once again, the actual volume of the molecules is very small compared to the volume of the container. So, I mentioned this earlier. While liquids and gases have measurable attractive forces that allows them to be a liquid and a gas, liquid and a solid, the attractive forces amongst molecules of a gas are negligible again. Gases can only be gases because they have that freedom. The gas molecule is free to move around in the container. The gas molecule itself is very small, very, very small. It almost has zero volume compared to the space it has available to travel in. But the gas molecule is free to travel around because there's no force holding it back. On the other hand, we mentioned this before, liquids and solids have stronger force of attraction holding them back, so they're not free to move around like the gas molecules are. And then we're told here the average kinetic energy of a gas molecule is proportional to its temperature, and the temperature expressed in kelvins. Remember I mentioned earlier that I was not moving that fast as an athlete. I mean, I was faster than the average person, but I wasn't the fastest in the room. Besides this one person, to tell y'all the truth, I was a second last, like second to last, and that's the best I could do. Okay, I was second to last in that room, and I wasn't moving that fast. But we're told here, unlike a person like me, the molecule speed relates to the temperature. So the average kinetic energy, or the energy the gas molecules has, is directly proportional to the temperature. That means at some point, if you recognize this relationship, if you want the gas molecules to move faster, apply more heat. And then the gas molecules absorb all that energy and they'll move a lot faster. I guess for a person like me, maybe you give me more caffeine and I'll be more energetic, because temperature is not going to really help, right? Then we're seeing right here, molecules interact with one another and with the container without loss of kinetic energy. I don't like the word they use here, interact, because it leaves it vague. Exactly how are they interacting, right? It kind of leaves things vague, but I already told you guys what it was. The molecules are bumping into each other and they're bumping into the wall. So when they say interact here, I'm like, what exactly is interact? This is just, it reminds me of the word entanglement right now, which, I won't even go into that. But interact here is just saying the molecules bump into each other. Right? Or they bump into the wall of the container. That's what they should just say, because interact leaves that vague, right? Exactly how are they interacting? So when the molecules bump into that wall of the container, they don't bump and then all of a sudden lose energy and stop moving around. When they bump into each other, the same thing. They don't lose energy. That collision, like when two cars bump into each other, the cars stop, right? That's called elastic collision. I mean, sorry, inelastic. Where they bump into each other, both cars stop, or they may move together. But molecules bump into each other and they keep moving as though nothing ever happened. Bump into the wall, keep moving as though nothing ever happened. Okay? So they don't let the collision influence their speed or cause them to lose energy. So I already mentioned this before, gas pressure. The pressure comes when those molecules hit the wall, and the greater the force. So here we're being shown the pressure, right? And how the pressure has to do with force and area. Now in physics, they usually define pressure as force acting on a certain point per unit area. For us, the molecule is hitting that wall. So the point at which that molecule bumps into the wall, that's where the pressure is being exerted, right? And it's just going off. The area where that force is kind of hitting is where you pretty much have the pressure being generated. So we're told here the effect of the force are the interactions on the huge number of rapidly moving molecules of gas as they collide with the surface of an object in contact with that gas, right? You get that force being generated during the collision. So it's all happening in the collision. They collide with each other, we don't get a pressure. But they collide with a wall, we do get a pressure, okay? So while we have pressure, what factors can influence this pressure that we see? Volume, amount of gas molecules, I should say here molecules, and then temperature. So we're going to go ahead and examine each of these. Now they don't go into that, but let me go ahead and add a page here. And I will go off and talk about each effect, right? So how is the volume affecting the pressure? I'm going to show you two different containers with two different sizes, and then we'll examine it. So we have the smaller container to the left. Smaller container, come on. We have the smaller volume to the left. And then we have a larger volume to the left. Then let's visualize our one molecule moving around. The one molecule moves from wall to wall, right? Colliding with the wall, moving a different direction, colliding with a different wall, right? Just like that. And then imagine the same molecule over here in a bigger container. Okay? So this is a larger volume, of course. So I'm going to ask y'all a question here. Which of these two volumes, the left one or the right one, will have a higher pressure? Y'all are extra quiet today. Yes, the left, right? The left has a higher pressure. Why? Because we have a greater pressure. Because we'll have a greater number of collisions. Collisions, if I can spell. Ooh. Is that how you spell? No, that's not how you spell collisions. Oh yeah, I forgot to tell y'all my spelling is horrible. Collisions, like that, right? Yeah. As the number of collisions increase, we have a greater number of pressure. Since the molecules are not slowing down, they're not being slowed down after every collision. They continue in the same speed, right? Greater number of pressure because we have greater collisions. And here on the right, we have less pressure. Why? Because we have less collisions. And why do we have less collisions? The molecules have to travel further than before. Molecules travel further. You are. Okay, let's go with that. I think that's the word. Further. Okay, we just examined volume. Let's look at the amount of gas molecules. So to examine the number of gas molecules, let me draw a smaller picture here because I'm running out of space. Okay, so two small boxes. We keep the volume right about the same. About the same. Okay. The left one has one molecule, the right one has got two, and they're both colliding against the wall. Okay. So this one here has got less molecules. Then the right one has got more or greater molecules. And here's the question. Which one will have greater pressure? The one on the left or the one on the right? Right, very good. Because we have more molecules, the chances of the collision is even greater, is doubled, right? We have double the number of molecules. Greater molecules, more molecules, therefore greater collision, because now you have two objects combining or colliding with a wall, and therefore we have greater pressure. Right? Okay, let's continue. I'll give myself some freedom and add a page. No, it's not like I'm cutting any trees. This is all electronic anyways. Okay, last one. We are looking at temperature. In the case of temperature, once again, you have to leave the other things the same, or else if you change too many factors, it's hard to really tell what is really causing the change we see, right? So we keep everything else consistent. I'll keep the size consistent this time around, if I can do that. The size of the container will be consistent. So I'll keep the volume the same. I'll keep the number of molecules the same. So I got 2. The one on the left, the temperature is like, let's see, 25 degrees Celsius. The one on the right, temperature is 100 degrees Celsius. So these are hot, okay? So I'll show this, and I'll show that, and I'll show this, and I'll show that. But how do you show speed? I'll just say fast. Right. So which one do you think will have a higher pressure in the container, left or right? Right, very good. The ones on the right are faster moving molecules, right? Very good. So remember, The number of molecules are the same. So the issue here is not really about the number of molecules, because we can argue, well, you have 2 over there, you have 2 over here. That's not the reason why we see a greater pressure. But we have a greater speed. So they're getting to the wall quicker and they're colliding with the wall more frequently. So with the higher temperature, this results in increasing number of collisions because we have more frequency, right? Increasing number of collisions. For that reason, we have, let's see, increasing pressure. The molecules are getting to the wall faster and colliding faster, so we're seeing all of this. Okay. And that's pretty much it for the illustration. We've done all these 3. Any questions about this? And so when we see that, we can then move on and see what they have for us in this next one. Oh, the mercury barometer. So the name here, barometer, meter just means a way or a means to measure something, like a metric ruler for measuring length. So we have a means to measure bar. Bar here, bar is actually a unit for pressure. So we have a device that is used to measure pressure. And so we're seeing here that the atmospheric pressure, P atmosphere, is equal to the pressure of the liquid in the tube, this tube right here, the pressure of the mercury. So years ago, many scientists were also monks. And that works because to be in science, you do have to dedicate a lot of time. So monks had a lot of time in between prayers. They will be doing science. So contrary to now, where there's a battle between, you know, science and religion, at some point it was the same people who were doing science who were actually monks. So one of the responsibility that Torricelli had was to fill containers, certain containers that were used to store water, with water. And the way the containers were designed, they had an opening at the bottom. Okay, so he will come in there and fill the container all the way to the top with water, and then some of the water will drain out. It will get to a certain point and it will stop draining out. And this happened from day to day to day. He thought the other monks were playing a prank on him. And then at some point he realized they weren't playing a prank. And so he decided to test the hypothesis to answer the question, why is the water draining out to a certain point? Why doesn't all the water just drain out? Why does it drain to a certain point, and then when it gets to a certain point, it stops draining out? And this happened night after night after night, to where some of the water will drain out, but not all of it. What was stopping the water from completely draining out? That was his question. So he went ahead and tested his hypotheses, his early judgments about what was happening. He realized it wasn't a prank, but there was a phenomena behind the scenes that was explaining why the water was draining out. He took what looked like a test tube, but it was graduated, meaning that it had marks on it, and filled it up with mercury. So he was also doing experiments, filled it up with mercury all the way to the top, like he did with a water container. He flipped this over into what looks like a petri dish. This container was originally full of mercury, but when he filled it over, the same thing happened with a water container, water reservoir container, where some of the water, or some of the mercury in this case, drained out, but it got to a certain point where it stopped draining out. The same thing happened. And he was like, what is it about this setup here that prevents all the water from coming out, or in this case, all the mercury from coming out? Some of the mercury comes out, but not all of it. Long story short, he realized it was the pressure coming from the outside, and this is the atmospheric pressure. So in the beginning, the tube will be filled with mercury, right? Placed in an empty container, empty dish. And at that point, well, I call it empty and then put some stuff in here. It's empty. At this point, there's no atmospheric pressure acting all around this container. Well, the liquid begins to flow out. When it flows out, and it flows until a certain point where the atmospheric pressure stops any more liquid from coming out. he measured the height of the amount of mercury left over, and almost every time he got a value. When he averaged the numbers, it was 760 millimeters. So now we say the pressure of the atmosphere, 1 atmosphere, is equal to 760, because after doing a bunch of experiments, he concluded that the atmospheric pressure was matched, or yeah, it matched the pressure inside the liquid, and the pressure inside the liquid will be at the height of 760 millimeters of mercury. So whatever the atmospheric pressure outside was, it ended up being equal to the pressure inside this container here. So they were equal to each other. Atmospheric pressure is now 1 atmosphere. The pressure inside the liquid, which is equal to its height, is 760. So you want to make sure that you have this equality here written down. Do you have to remember the story? No, this is just a FYI. This is how we got to this place and we got to this number. What you want to have, though, is this number here. 1 atmosphere equals 760 millimeters of mercury. Sometimes they use that unit, or they say 1 atmosphere is equal to 760 torr. So the scientist Torricelli was the one who came up with this relationship. He wanted his name, the shortened version of his last name, to be used as a unit of measurement. So we call it torr, or millimeters of mercury. We have discussed the property of gases, right? The exerted pressure, they occupy space, volume. They do have an amount. They do respond to temperature. So I won't go into all of that stuff. What I do want to focus on here is the relationship between pressure and volume. So at some point, we'll see this relationship. The pressure is inversely proportional to volume. The greater the volume you have in the container, the less pressure of gas in that container. So based on this relationship here, if you have a very, very large volume, you will have less pressure from the gas inside the container, because it takes the gas molecules longer to get to the wall. If you have, the next relationship we have here is pressure and amount, right? The amount here, usually we use the term moles to represent the amount. So if you have a greater number of moles or particles, we saw that we will have a greater pressure because we have more collisions. Next one, pressure and temperature. Pressure proportional to temperature. What does that mean? This means if the temperature of the gas is increased, we get greater pressure. This is a summary of what we've seen so far, right? And it's been summarized here before, or here below. Any questions about that? So I already told you guys about the 1 atmosphere is equal to 760 millimeter unit. Make sure you write this equality down. You want to have that for future calculations. We see the one with the torr, like I was telling you about. Remember that 1 torr is the same as 1 millimeter of mercury. So make sure you have this written down. And then we have other conversion units for pressure. We have 1 atmosphere is 101,325 pascals. We also have 1 atmosphere equal 101.325 kilopascals. Okay, so just remember, you want to have these units in place just in case you have to do a conversion and you need one of these. These will be available to you. So I've highlighted all the units you need to write down, all the conversions you need to write down. If you're converting from one unit of measurement to another, you're going to be needing these conversions. These are the most popular ones depending on, the questions you have out there. If you do have questions where the conversions required are not here, you can just go ahead and find them online and see what the conversion factors are, because the list I gave you guys last time is not comprehensive. It does have some, but not all the possible conversions out there. Okay. Once you have all that, they're giving you more conversions here. Okay. They do have one in atmosphere. You know what? This one here we barely use, so I'm not going to highlight that one. We do use this one here. Oops, wrong utensil. Right here. Okay. So if you need to go from atmospheres to PSI, use that conversion. Okay. I'm trying not to spend a lot of time on just the FYI information. With this part, the part that you need to know is the open-ended manometer. So we have different ways of measuring the pressure. Depending on what kind of pressure you're measuring, you have your blood pressure for the person. You have your atmospheric pressure. You have the pressure of the gas. And so we have different devices that are available to measure all these different pressures, right? And so what we're going to do here is we're going to be looking at how to measure a pressure or determine the pressure of a gas using what is called the open end manometer. So manometer is a device used to measure the pressure of the gas, used to measure pressure of gas. Okay, so I'm not going to be explaining all the stuff that's over here. I'm trying to skim through to see how important this detail is. This part here is just the gauge pressure. If you have to ever measure the pressure of your tire using that thing, the tool that looks like a pencil, you're going to be reading the gauge pressure from that. The absolute pressure here is the pressure that we rarely ever use, but it happens to be listed here. But you do have to be aware of the gauge pressure and then the pressure of the gas from the open end manometer. So I want to go straight to that, the open end manometer, because this part is important for your homework and for the lecture. So over here, with the open end manometer, they actually gave you equations. Okay. In the previous slide, you didn't really have an equation. I was just thinking about it. We do have some questions. I'll try to find those for next time. But this shows you how to find the pressure of the gas. So normally, we used to have a round bottom flask on the left right here. That's okay. We use the Elemiah flask right now. The picture on the left here shows us what looks like a J-shaped tube. Sometimes it's J-shaped or U-shaped. And so the J-shaped tube starts off being filled, not filled, but kind of half full with mercury. So it looks something like this on the right. I'll draw this like that. Okay. And then one of the open ends is attached to the Elemiah flask. And when it's attached to the Elemiah flask, then the gas is generated in the flask here. It travels all the way through, and then it pushes against the liquid. So before, this liquid here was at the same level, like that. Once and they made the gas yellow. Once it travels through here, the gas begins to push against the liquid, and this gets down here, this gets up here, because you have the pressure of the gas coming and pushing against the liquid, almost forcing the liquid out of the tube. Okay, so I drew the meniscus wrong by drawing it like that. This is mercury, so it's more like this. Okay, mercury has an upside down meniscus. Okay, so we now are dealing with three pressures. There is a pressure from the gas molecules inside the container, and this is called P gas. There is a pressure because we now have a height difference, the height here and the height here, of the liquids inside the tube. This is called a pressure due to height. Over here, though, they call it pressure for mercury. It's the same thing. The difference in the height of the ends of the mercury, so the meniscuses, right? That gap between them, that's called pressure of height. And then coming from the outside in to this other end, this is the pressure of the atmosphere. And this picture is called PA. Okay, so let me go ahead and get a fresh page and then show you guys how I generate this. Okay, y'all are extra quiet, like extra quiet. Feel free at any point, don't be shy to ask me any question. So I'm going to draw my picture. It won't be as good. I'm just warning you right now. You know, give me freedom to now use this better looking container. It's a lot easier to draw. So we have this right here. Oh, not bad. Okay. Okay. Let me scoot my picture down a little bit lower. Okay, right there. So remember before we had the liquid in here, the mercury, at the same level. Once the gas got generated, the mercury shifted. So the one here on the left went further down, then the one on the right went further up. So now this is the area where the mercury is occupying. Okay? And then we went from having no difference in height of the liquids inside the tube to now we have a difference. We have a higher point and a lower point. And the difference in the height of the liquid is essentially the same as the pressure of mercury. From the outside, we have the atmospheric pressure, the gas pushing inside into the container or the tube. Then from the container here, we have gas. Okay? So this is called P gas. So before we get to the equation, I want to ask you guys this question. Based on the picture, if you look at the pressure of the gas, oops, if I can spell gas, GAS, versus the pressure of the atmosphere, which is stronger? Which is pushing more against the liquid inside the tube? Is the pressure of the gas pushing further down on the liquid or the pressure from the atmosphere? We're trying to compete these two here. Have a competition between the two. Is P gas stronger than P atmosphere or is it the opposite? What do y'all think?
I think the P gas.
Okay, very good. It's P gas, right? So why is the P gas stronger? What does it look like it's stronger?
Because it looks like, on the side it's, I don't know, like, I don't know,
It's
you can
pushing
just
further
see it,
down?
like, down. Yeah.
Right, exactly that. It's pushing further down. So between the two. So when you're writing out your equation, even though they gave you one, the way this section works better is if you actually look at the picture and let the picture tell you what the equation is. The greater pressure will be written on its own. So in this case, of the two, P gas will be written by itself, and it's equal to the sum of the two lesser pressures. So P height or P mercury plus P atmosphere. So the greater of the two will be by itself on one side of your equation. On the right, you have P height plus P atmosphere. And that's how you get your equation. So while this is provided for you here, I'm not saying it's wrong. I'm just telling you that this formula here may not always be useful, right? Let me mix it up a little bit. What if we have this a similar scenario here, and then we have a container? This container is going to change shapes because it's just based on how comfortable I am drawing this. Just ignore the shape of the container. The biggest thing is what's happening in the tube. What if the tube has this going on right here? P gas and then P atmosphere. How will I write my equation this time? This is what I'm focusing on. And everything is said and done, and these happen to be at the same height. How will I write my equation? Which of these is larger or stronger, P gas or P atmosphere? Think about it. Think outside the box. Which is stronger? Before we said the stronger one was pushing more further down on the liquid, right?
Yeah.
So which one is stronger in this picture here? Is P gas stronger than P atmosphere? And is P atmosphere? Oh, sorry. I'm focusing on hearing you say something. My bad. I see you written it there. It is equal, right? So for this one here, your equation will be P gas equal to P atmosphere. I was wondering why nobody was answering. Okay, yeah, P gas equal to P atmosphere, right? So you can't just memorize. So at this point, we can say P of H is equal to 0 because there's no height difference. P of H is only generated when there's a gap in the height of the mercury inside the tube. So don't just blindly follow the equation here, even though it was provided. You want to be aware of how we get the pH, right? From this picture here, just looking at this picture, we can say The pressure coming from outside, P atmosphere, is obviously stronger, right? Because it's pushing further down on the liquid. So in the equation, it would be by itself. P atmosphere equal P gas plus pH. So I've actually shown you how to get 3 different equations. This one here, and the equations are written based on the picture and how we have different levels or maybe even same levels for the mercury inside the tube, right? And then they'll give you numbers here and then you plug and solve for it. That's it. But the most challenging part in this section here is knowing what equation to use. And you want to look at the picture to determine that. Okay. So remember how we saw all those equalities and conversion factors? Now we're seeing, okay, we have to work this out. Now what I usually do, like before, not here, is to add a blank page so I can work everything out from scratch, right? Even though it's been worked out. The pressure inside a steam boiler is 14, so 1427 psi. This is the pressure inside. Express this pressure, so convert this to atmosphere. So at this point here, you want to go to your conversion factors, and you find that 1 atmosphere is equal to 14.7 psi. So I had you guys copy this earlier, right? If you haven't copied it, go ahead and copy it now because it's obvious we're needing it here. That means it might be important in the future. This is my conversion I'm going to be using. Just like we did before, set up your, write the number given to you. Oops. This is going to be 14.27 psi. Draw your conversion brackets. Take your equality and make your equality your conversion. Since we have psi up here, you're going to have psi down here. The number that has psi in your equality is 14.7. On top, since these numbers are a combo, they go together, you have 1 atmosphere. Now it says right here, convert until you get to ATM, then stop. That's what it means. When we cancel these units out, we are ATM. How do we work this out mathematically? 1427 times 1 divided by 14.7. There is no scientific notation here, so you're just plugging and chugging, and then you're getting your answer. So I have my calculator here, 1427 times 1. Yes, I actually did that. Divided by 14.7, and I get 14.7. And I get 97.07. Okay, let me see. I need to check and see the numbers they gave me. They gave me 4 significant figures, right? This is my only given number. This is 4 significant figures. Since I'm multiplying, my answer has to have 4 significant figures. So this would be 97.07 ATM. This is also 4 sig figs. Don't use your conversion sig fig to figure out your answer sig fig, because what if you use a different conversion factor? In chemistry, one of the underlying goals is cohesiveness, so that everybody's at the same place at the same time. So we usually use the significant figures of the given number, not the conversion number. Then you want to match that with your product. Okay? And that's it for that question. And this one here, okay, I'm just skimming over it. I'm seeing a lot of words. That's okay. Let me find my, where is the slide? Here. I'll add a page at the bottom. Okay. The pressure in an automobile tire is 29 psi. So right here, given 2929 psi. That's the pressure. On a day when the weather report states that the barometric pressure from the weather, okay, barometric pressure is 30.09 inches in mercury. Seriously, we use millimeters of mercury. Anyway, how would you report the absolute pressure? Oh, okay. How would you report the absolute pressure in the tire to a colleague in Canada in KPA? So they want us to get absolute pressure. And then we actually get this in kPa to report it to a colleague who happens to be in Canada. I don't even know how they got there, but that's besides the issue. So absolute pressure, the formula for that was back here. I saw it. Yeah, absolute pressure is the sum of the gauge pressure, that's the measured pressure, and the atmospheric pressure. So add these two, and then you get absolute pressure, right? So let me see what the gauge pressure and the atmospheric pressure is. Oh, we already did this one here. So yeah, this is the gauge pressure, and this is the atmospheric pressure, right? So absolute pressure is the sum of these two. But you can't even add these two until each one is in the correct unit, right? You cannot take, so let me write here, absolute pressure is equal to gauge, how do you spell gauge? Gauge, oh, there it is, plus atmosphere pressure. So I write the pressure down here, pressure down here. Now our numbers are 29 psi plus 30.09 inches of mercury, right? We can't really just add these two numbers because their units are completely different. Let me see. I guess they go ahead and work it out here. Okay. Since we're going to go ahead and get our final answer in kPa, they want this in kPa. Our plan should be to go from psi to kPa for this number on the left, to go from inches of mercury to kPa for this number on the right. So we're going to start with the left one. We're going from psi to kPa. So in the other conversions, when you're doing these conversions, I'm just going to tell you right now, you want to almost convert to atmosphere before you convert to something else. Atmosphere is kind of like the mix master. Like if you're trying to go from, let's see, North Dallas to South Dallas, you go through downtown. So downtown area is kind of where the mix master, where a lot of streets meet. When you're doing pressure conversions like this, you want to convert to atmosphere, and then it's easier to get from atmosphere to the next one. Okay, so I'm going to need y'all's help on this one. 1 atmosphere is equal to 14.7 psi, right? So let me quickly map my units. The psi here matches the psi, the starting point. But atmosphere does not match kPa, right? I think I had you guys write this down. 1 atmosphere is equal to how many kPas? I think you wrote it as 101.325, right? If you didn't write that down, go ahead and write that down. So you see that we need that here, right? Like I told you, atmosphere is that good place to convert to. And if you're there, it kind of helps you navigate around. So you see the kPa here matches my wanted unit. This matches my given, and these intermediate ones match each other. Okay? So I'm going to go ahead and convert this first one to go from psi. So I'm converting this number up here, 29. Okay, so I start with that. That's my goal. 29 psi. So I'm starting with 29. Let me see. My conversion on the bottom has to have psi in it. So I look at my numbers. I have these two to pick from. This top one here has psi in it, so I write 14.7 on the bottom for my psi. On top, I have 1 atm. Because remember, they're a combo deal. The unit you pick on the bottom has to match the unit here so they can cancel out. Now the dominant unit is atm. I'm done using this first one. So whatever I put on the bottom, the number, it has to have the unit atm. So atm, that's going to be this number here, right? The 1 goes with atm. It's a package deal. So I have to use 101.325 kPa. Okay? So in doing this, You can see the unit kPa remains undamaged or anything. PSI cancels out. ATM cancels out. Whatever I have left, once I'm done with my math, I'll be left with a number that has a unit kPa. Mathematically, this is what I'm doing. 29 times 101.325 divided by the bottom number, right? You multiply the top numbers, divide the bottom number, 14.7, and whatever I get goes over there. So let me see, what do I get here? 29 times 101.325 divided by 14.7. Ooh, okay. Down here it's showing me 199.892. Let me see. I'll leave it like it is right now, not mess with it, because I'm going to be doing some math here. 199.892. Yeah. So this is my half. I need to add more space. Yeah. So this is my top number, right? So I just converted that to kPa. Now I have to convert this to the number right here. 30.09 inches of mercury. Okay. Man, they made this interesting. So to convert 30.09 inches of mercury, I have to convert this to kPa. Okay, because inches is the length, right? So I don't know how many inches there are in one atmosphere. What I do know is, let me start with what I know. I'm going to write my conversion here. One atmosphere is equal to 760 millimeters of mercury. Okay? This I know, but the unit here is millimeters, not inches. So do I have a way to go from inches to millimeters? Not exactly. I'm going to try to make this as difficult as possible. No, not exactly. I do know, however, that 1 inch is equal to 2.54 centimeters. Remember this from before? 1 inch is equal to 2.54 centimeters. This has inch here, but not millimeter. I need one more conversion. How do I go from centimeters to millimeters? Is it safe to say 1 centimeter is 10 millimeters? Right? Y'all are extra quiet, so you're probably like, what? Let me see. Do I have? I didn't realize I was going to need so many conversion factors here. At some point here, I have my conversion. Let me see if it's still there. Oh, there it is. Can I make this bigger? Okay. So you see, when it comes to the length, do I have millimeters here? No, I don't have millimeters. Well, I kind of do. Oh, there it is. Okay. So remember, the unit of mercury for 760 is millimeters of mercury, not inches. So I have to go from inches all the way to millimeter. Now, I didn't really have a direct relationship. So I went with, let's see. The idea was to go from millimeters to centimeters using this conversion here. So I wrote this down. 1 centimeter equal 10 millimeters. So I'm using that. And then once I get to centimeters, I can go from centimeters to inches using this relationship right here. Now I kind of worked backwards, but you get the idea. We're trying to go from inches to millimeters, and we're going to be using these two conversions here to accomplish it. Okay, let me minimize and go back to my right here. Okay. So my goal is to go from, once again, inches of mercury, eventually to kPa. I'm nowhere near kPa. So let me show you how I'm mapping my units right now. The inches of mercury matches with this unit right here. My centimeter, I'm going to convert it to, matches with the centimeter here. My millimeter takes me to this. But once I get to ATM, I have to be able to go from 1 ATM to 101.325 kPa. Okay, since I have all of this, let me try to go in order so that as you're looking at this, I'm gonna relist this list in order so y'all can see how it works out on the right. So I'm gonna start with inches of mercury, and my goal is to go to kPa. So I look in my list and I find out that 1 inch can actually convert to centimeter by using this conversion here. Okay, so I just rewrote that. But when I get to centimeter, I'm not a kilopascal. So what do I use next? I use this one here. 1 centimeter can get me to 10 millimeters. And so I guess I can say here 1 inch of mercury can get me to centimeter of mercury. 1 centimeter of mercury can get me to millimeters of mercury. I'm still not there. Then I'm going to be using this one here. 760 millimeters of mercury can take me to 1 atmosphere using this conversion. Once I get there, 1 atmosphere can take me to 101.325 kilopascals. So that's the plan. That's what I plan to do. It just requires me using all of these conversions. This was a very interesting question. So I'll start 30.09 inches of mercury. This is my given number. I hope I can use all of these. So I write this down. The next conversion I'm going to be using is this one here, right? Because this has inches of mercury. I'll use 1 inch of mercury down here. I'll use 2.54 centimeters. I just added the mercury because the focus here is mercury, right? I just use that. Inches of mercury cancels out with inches of mercury. Then, since I have centimeters of mercury, I have to put centimeters of mercury down here. I get to use this number next. 1 centimeter of mercury. Top one is going to be 10 millimeters of mercury because this is what comes next, right? This and this cancels out. Now we need to get millimeters of mercury in here. That's going to be this one here. 760 millimeters of mercury. That goes with 1 atmosphere. This and this cancels out. Finally, 1 atmosphere goes with 101.325. Wow, that was quite a trip. Atmosphere and atmosphere cancels out. So you see that I picked the conversions to help me go from where I was to where I needed to be. So the math, I take 30.09 times 2.54 times 10 times 101.325 divided by all the numbers on the bottom, 760. And our answer will be some number, kilopascals. Oh no. Right. So let me do the math here. Oops. And see what we have. I think they use a much direct conversion. 30.09 times 2.54 times 10 times 1.01.325 where's my divide by 760. Okay, so I finally get 101.9. This is what I get here. Kilopascals. So you need to add these two numbers, right? The numbers I got, I need to add this. Oops, wrong thing. I need to add this number here to, where's the other number? This number here. So when I take that and I add it to 199.892, what do I get? So it's showing right here, when I add those two, I get 301.7. So when you round it up, this is kilopascals. Let me see how they wrote their answer. Oh, they rounded it up. That's okay. They rounded it up to scientific notation. So this ends up being 302 kilopascals. Scientific notation, this will become, remember, 302. Take the decimal back here, move it 1, 2, until you have one non-zero number to your left. You end up with 3.02 times 10 power, let's see, I moved 2 spots, 2 kilopascals. And so they have two one decimal place, two significant figures. So when you do it that way, you end up with 3.0 times 10 power 2 kilopascals. So we kind of use all the things that we learned before in the previous chapter, but essentially that's how you get this. Now, they had a more direct conversion, not like the one I did. If you have a direct conversion, go ahead and use that. They had a more direct conversion to go from inches to kilopascals. I don't know where they got this from, but hey, write this down. Why not? You don't have to make it really long and detailed. You don't have to. Just get these conversions and you can use these directly to go from one unit to another. I don't have these memorized, obviously, so I'm going through it step by step, right? But that's how they get the values. Now we're going to be going over the gas laws with the remaining time. Before we go over the gas laws, please recognize, I won't go over absolute zero here. We're going to start with Charles' law. So as far as the gas laws are concerned, we have three laws that you guys cover, and then we cover the combined gas law. So in gas law, in Charles' law, they're showing you what's happening here. And this is just illustrating to you two different scenarios, which is, it's kind of hard to really see this very well. So let me go ahead and draw my own scenario, because the picture that they're showing you here is not a very, it's kind of hard to see. Even if I show you right here, it'll be a little bit hard to see. Charles' law talks about two things. So in general, let me give you the general overview of gas laws. With gas laws, we compare four properties of the gas. We're going to be looking at Charles' law. We'll be looking at Boyle's law. And then I think you guys go over Avogadro's law. Yeah. So Boyle's law, then Avogadro's law. And at some point, we're going to combine all three. So for us to study the gas law, we compare four properties of gases. I'm going to summarize it here. Four properties of gases. Oops. Combining my letters now. Of gases. And these properties are pressure. You're comparing this with volume, temperature, and moles. And so what they do to figure out the different laws is, even though these four properties of gases are being studied, two are compared and two are kept constant. So in general, two properties are compared to each other, while the other two are kept constant. Okay? So two are kept constant, the other two are compared to each other. I'm realizing how I'm writing and my writing is not straight according to my iPad. That's okay. These are the small things I noticed, and I'm like, why is it not straight? It's okay. Okay, so let's go ahead and start. And if we're going to be starting with Charles' law observes the behavior of volume and temperature. So in Charles' law, volume is compared to temperature when moles and pressure are kept constant. And so the idea is, you're looking at Charles' law, you compare volume versus temperature. Number of moles and pressure, these are kept constant. And what is the expected behavior? Well, scientists notice that the volume is directly proportional to temperature. That means if the temperature increases, volume also increases, right? That's what a direct relationship means. If the temperature increases, the volume also increases, as long as the number of moles and the pressure remain constant. So when I was looking at that picture, this is what I was looking for. Are they showing us this relationship? If they're not, that picture is of no use to us. I was trying to see it and I was like, man, these in here are so small. It's supposed to be showing us how volume is influenced by temperature. So remember we said in the container, if the molecules have a greater temperature, they're going to be colliding against the walls of the container. So we're going to be seeing why the volume increases. Yes, they're showing you this right here. Like I just mentioned, the volume of the fixed amount, so they're saying here, the volume of a fixed amount of gas, meaning number of moles is constant, at constant pressures. They said it right here. Number of moles is constant, P is constant, is directly proportional to the absolute temperature. By the way, absolute temperature here means the temperature is in Kelvin. Okay? So, yeah. Oh, I'm glad I mentioned it here. The proportionality sign can be changed to an equality by inserting a proportionality constant. This means that we can change this expression here, called expression, to an equation by making this equal to. So this K gets introduced, and essentially the proportionality sign gets replaced by this whole expression right here. Okay? So you replace the proportionality sign with this right here, and automatically we get an equation. And so if we have that, it's just saying V over T equal K, and this is constant. So what y'all need to remember is, remember the statement, remember this part here, and then you want to remember the equation. That means if you are able to measure the volume and the temperature at two different conditions and divide them, you will get the same number each time. So you want to get this equation out of that. This is the equation, what I wrote down here. This is the equation you're going to be using to solve problems in the future. What I've highlighted here in the statement, the law generates this equation, the expression showing you how volume and temperature are related. But down here, this is the equation that you use to solve problems. Temperature has to be converted to Kelvin all the time. Okay? So once you have that down, oh yeah, they eventually lead to this equation here. So once you have that down, then we have a practice problem. In our practice problem, let me go ahead and add a page down here so I can write. We're told a container with flexible walls holds a gas that is cooled from, so we have a container, it has flexible walls like a balloon, has a gas that's cooled from temperature initial. The first temperature provided to us is 65 degrees Celsius, first temperature. And this is cooling to the second temperature, final temperature, is 22 degrees Celsius with no change in pressure. Okay. If the volume of the container was, so initial volume, volume 1, oh, let me make this 1 versus initial. Volume 1 was equal to 4.5 liters initially. What is the volume after being cooled? What is V2? I don't know. The V2 is going to be in liters also. Okay. So remember, we just wrote the formula down for solving this problem. V1 over T1 equal V2 over T2. So we do need the temperature, though. They said this before, but I want to say it again. The temperature has to be in Kelvin. In Kelvin. Now, we mentioned this in the previous chapter, right? To go from degrees Celsius to Kelvin, Kelvin is equal to whatever you have in degrees Celsius at 273.15. Remember this conversion factor right here? The temperature conversion to get a Kelvin, take the degree Celsius at 273.15, you get Kelvin. So you want to have that right there. So I'm going to highlight that. A formula you should have in your list of things. So I'm going to use this formula here to convert all my temperatures to Kelvin. So going back to this top one here, let me move this to the left, out of the way. I mean to the right, not the left. This is to the right. Okay, I need this in Kelvin, so I'm going to add 273.15 here to get this in Kelvin plus 273.15 to get my numbers in Kelvin. It's going to be what? 65 plus 273.15. I get 338.15. On the bottom, 22 plus 273.15, I get 298.15. These are both Kelvin, right? So now I can use these numbers I have here and plug them in the formula to solve for this one. Okay, I'm trying to get V2, this V2 here. So I'm trying to get that. Let me go ahead and get it by itself. So to rearrange, because this part is tricky to some people. If it's you, don't worry about it. Times T2 times T2. I'm trying to get V2 by itself because we're trying to solve for that. Cancel this out, cancel that out. So we have T2 times V1 over T1 is equal to V2. What I have to do here to solve for V2 is to plug everything in. Do I have T2? Let me scroll down here. Yeah, it's 298.15 Kelvin. Do I have V1? Yes, 4.1 liters. Divide by, do I have T1? Is that 338.15? Yes, I got that. So the K and the K cancel out. So let me see, what do I have here? 298.15 times 4.5 divided by 338.15, and I got 3.9, liters. Okay? Does it make sense though, this question? The answer I have, does it make sense before I quickly go check and see if I'm right? I better be right or somebody's going to be called. Let me go back here and see. We started off with something that was really hot, and then it was cooled, right, to a much cooler temperature. Temperature gets colder. Our molecules are sluggish. They're moving a lot slower. They can't make the container's volume expand because they're not even colliding with the container that much. So for that reason, we expect less volume. Let's see what they got. Oh, let me see how many significant figures. Oh, okay. We gave it 4.5. That's two significant figures. So I need to watch out for that. Let me label this right here. This is two significant figures. So my answer has to be rounded up. Is this, do y'all get 3.96? Because if I do it that way, I end up with, yeah. Oh, you know what they didn't do? They didn't use, okay, I end up with 4.0 liters. They probably didn't use the 0.15 here, but they did it before. That's fine. Our answer is very similar to theirs, so it should be fine. Yeah, they didn't use a 273.15. Y'all see that? If they had, their number would have been closer to ours, but it's still consistent. When the temperature decreases, it leads to a decrease in volume. Okay? So everything looks good. Then over here we have a picture that's showing us, we have even a graph here showing us pressure and volume relationship. And pressure and volume have an inverse relationship. Just saying that if you look at this graph here, the y-axis is pressure, the x-axis is volume. When the volume is around, is this 7? When the volume is 8, the pressure reads as what? Let me try to read this pressure. Around 850. So let me say this. When the volume is 8 milliliter, pressure is equal to 850. Is this number 2? Let me look at here. I don't even know if I can read this. I can read that. When the volume is 12 milliliter, the pressure is, can I read that? Around 560. So as the volume gets bigger, the pressure is decreasing, showing us that we have an inverse relationship between volume and pressure. So when I was learning this years ago, I used to call it the VIP law because it looks like VIP. Okay, right here. So the graph shows us that when the volume is decreasing, the pressure is getting bigger. Because remember, the volume of the container decreases and the molecules hit the wall even faster. And then we have this relationship here. So we start like before. Let me start in the beginning. Volume is inversely proportional to pressure. Replace the proportional. Replace with equal K. So volume equal K 1 over P. Multiply both sides. To get the K by itself, multiply both sides by P. Multiply both sides by P. This cancels out. We get P times V equal K. Then they just do P1 V1 equal P2 V2. You're not required to know how we go from the beginning to this part, but I'm just trying to show you how we get to that part. This is the equation you're going to be using to solve problems. P1 V1 equal P2 V2 for Boyle's law right here. Okay, give me just a moment. Okay, and I am back. So when we look at this equation right here, remember, you want to remember the statement of law, which is written down here on this slide. Okay, which says, when they say for a fixed amount, they're referring to number of moles of gas. Remember, in this case here, in the Boyle's law, we're saying, when we're looking at pressure, volume, number of moles, and temperature, in Boyle's law, we focus on pressure and volume relationship. That means number of moles and temperature has to be constant, right? So we see that volume is inversely proportional to pressure, and then you keep number of moles and temperature constant. So these other two have to be kept constant. So whatever changes we see in the pressure, we can blame them or we can attribute them to the volume, right? Because only these two things are allowed to change. Number of moles and temperature have to be constant. So they say so even in the law. For a fixed amount of gas at constant temperature, fixed amount of gas, this is the amount, temperature constant, this is the temperature. At two different pressure volume conditions, we have P1 times V1 equal constant, P2 times V2 is constant. So the law is just saying these will be inversely proportional, but of course P1 times V1 equal P2 times V2, okay? So the volume and the pressure will be inversely proportional to each other as long as number of moles and temperature are kept constant. So I'm seeing that they didn't really explain the law that well, so let me go ahead and write that here in a summary. For Boyle's law, do I even have room to write? Let me erase this from here. Yeah, because these slides are kind of all over the place. Boyle's law is just saying the volume of a gas is inversely proportional to the pressure when moles and temperature are constant. So keep the moles constant, right? Because that's what we say here. Keep moles constant. Moles has to be constant. Temperature has to be constant. And only then will we see the volume and the pressure inversely proportional. So I know we're doing content. Let me break it up a little bit and give you guys some stories. This is a 1405 class. See, I can get right into it and I can just keep going. So real quick with the stories. Charles Law. We see Charles Law applied in real. I shouldn't call this real life. This is also real life. Life outside of chemistry boundaries, the lab. On a hot summer day, the 18 wheelers, right? That's what they're called. They have 18 wheels. They really do have 18 wheels, right? So the 18 wheelers are out there, they're driving, and you know they have 18 wheels, like I said. Does anybody know why they have so many wheels? Has anybody tried to count the wheels that's willing to admit it? But do you know why they have so many wheels? It has to do with Charles Law. So this is not a far off question. Most of the 18 wheelers are carrying cargo, right, and transporting across states. Some states are cold, some states are very hot. But the question is about a hot summer day. Does anybody know why they have so many wheels?
No.
Really? Y'all not curious? When I heard they had 18 wheels, I was like, what? Yeah, I'm the kind of person who sat there and counted. I didn't stick my head under any of the wheels, but I'm just going like one, two, three. They really do have 18 wheels. And many times I've driven behind an 18 wheeler where uh, a few of the wheels, I mean, the spokes and the whatever, the metal part is still there, but the wheel is just gone because it bursts. So what happens on a hot summer day is you have a fixed amount of gas, right? A fixed amount inside tires. On a hot summer day, as the tire is in contact with the very hot road, the gas molecules inside of the tire are getting hotter. They're absorbing heat from the environment and they're getting hotter. Well, gases do what gases do. This chapter is all about the gas molecules. So they're colliding with the wall of the container. Now, in Charles' law, the temperature can make the gas molecules collide more with the wall of the container. If the wall of the container is flexible, the wall of the container will expand to accommodate the gas molecules colliding with it. So as the temperature increases, what happens as a result of that is the volume will also increase, but the increase in volume is only happening because the gas molecules push more and more and more against that volume. Eventually, the volume expands. But tires from 18 wheelers do not expand. It won't even work if they can expand. So as the gases get hotter and hotter, they collide against the walls of the tire, but the tire refuses to expand. So it happens until eventually the tire bursts. Since this is very common on the highway, they have a backup for every tire. So every tire, besides holding the load, is a backup for the tire next to it. So it's very easy to see an 18-wheeler lose a wheel. I've seen it happen when I'm driving on the highway. I drive a lot, and I'm like, whoa, okay, I go the next lane, but it doesn't slow the driver down. He doesn't even notice it for a while because there's a backup wheel. Okay. So if you don't have a flexible container, the whole tire bursts, and the tire is not flexible, so it bursts. And you see pieces of tire on the street, on the highway during a hot summer, like the one that we have in Texas now. I wouldn't know. I'm not driving much because I'm at home, right? In Boyle's law can be explained well by we are all alive right now, so we're breathing, right? I don't want to get into the biology so much, but with the Boyle's law here, essentially, as the pressure increases inside the container, it alters the volume. So here we're talking about the inverse pressure, right? Inverse between the pressure and the volume. So I want to talk about your lungs right now. Yeah, in a time of corona. We have lungs. I'm going to try to draw a very nice picture as I can. The best picture, not the best picture, but this is the best I can do right now. So we have lungs, okay? And then these lungs are housed in your rib cage. So the pressure we're talking about is the pressure outside the lungs, right? So we have oxygen in here as you're inhaling and then you're exhaling. So what allows you to inhale? If everything is okay, what allows you to inhale is actually the diaphragm here. When you inhale, your diaphragm actually, oops, it doesn't disappear. No, this is miscommunication. Uh, your diaphragm actually drops when you inhale. It drops from the bottom, and then the volume around your lungs increase. And when that increases, it allows these molecules in here and your lungs to get bigger. So when the volume around your lungs increase, the pressure here, pressure decreases. So the volume in the rib cage increases. The pressure in the rib cage decreases. And so this is the part that is Boyle's law. You inhale, your diaphragm drops, then the area around the volume increases, the pressure decreases. When the pressure decreases, there is less external pressure squeezing your lungs and making it smaller. So when this pressure decreases, I can erase all of this right here. Your lung will actually expand and more air from the outside will come rushing in. And you inhale, and that feels good. When you're ready to exhale, which is happening automatically, your diaphragm drops back in. The volume here around your lungs decreases, so volume goes down. And when the volume goes down, the pressure increases. So the pressure increases is kind of like squeezing a basketball. It squeezes your lungs, and then the lungs become small again and forces the air out. So as we are inhaling and exhaling, we are actually illustrating how Boyle's law works. Okay? Boyle's law is a relationship between the volume and the pressure. So if there is a greater volume, there's usually less pressure. Don't ask me about how the ventilator works. Does anybody want to know how the ventilator works? And why they say it's kind of dangerous? I said don't, and I'm asking you, right? But okay, essentially the ventilator does force air into the lungs. It's very hard because they say that, now mind you, disclaimer, I am not a nurse. I just teach chemistry and I happen to read a lot. But the idea is the atmospheric pressure is about 1 atmosphere, right, of air. And the ventilator pressure, they try to get it very close to the atmospheric pressure, the pressure that we're normally used to inhaling, but it's hard to get it that at that pressure. So it's usually higher than the atmospheric pressure. And then you're forcing air at a higher pressure down people's lungs. So that usually overworks the lungs. Even though the goal is to keep you alive, it overworks the lungs. So while the ventilator helps, it also hurts your lungs, if that makes sense. And that's the only thing I'm qualified to say because this is in line with Boyle's law. Beyond that, I am not licensed to explain. Okay. So the air that we are comfortable breathing and inhaling is the atmospheric pressure that we have around us. Okay. So we do have a question here, and this question here is talking about active exercising and stuff like that. So we'll go into exercising. But there's a lot of interesting stuff that's happening right now in the world of science that relates to what we're learning in class. I try to not get lost in the details though, because I can do that. A gas sample occupies. So we have a volume here. The first volume we provided is 5.18 liters at a pressure. The first pressure we see, which I'm assuming corresponds, is 776 torr. So we have 5.18 liters, 3 sig figs, 776 torr. They're telling you find the volume of the gas, okay? Find V2. I'm assuming the volume is going to be liters. It didn't say otherwise. If the pressure is changed to, if P2 is 827 torr. Okay, I'm going to get a brand new page down here. That's okay. I won't use a lot of it, but it should be good. So we have V1 being 5.18 liters, P1 being 776 torr, V2 being whatever it is liters, and then P2 being 827 torr. Okay, let's see. We said P1 V1 equal P2 V2, right? So we're trying to solve for V2 this time. To get V2 by itself, divide by P2 both sides of the equation, and then we're left with P1 is V1 over P2. This is equal to V2. Okay? So here it is. We have this right here. This is our equation. So do I have my numbers? The only Charles law is the only one that requires you to convert the temperature to Kelvin. There's no temperature here, so we don't have to convert anything. I just plug and chug. So over here, my P1 is what? 776 torr times, I use that, V1, 5.18 liters, divided by P2, 827 torr. Okay? So torr and torr cancel out. My answer should be in liters when I work this out. So I'm going to take my 776 times 5.18 equal divided by 827. So when I plug this in, I'm taking 776 times 5.18 divided by 827. What do I get in liters? 4.86 liters. Okay, this is the answer I get. Let me see how true this answer is. I'm going to check their answer. Oh, their answer's on the bottom. Yep, that's where they get it. Right. So the pressure is increased. If the pressure is increased, the volume should decrease, right? We went from a lower pressure to a higher pressure, so we expect it to go from a higher volume to a lower volume, and our final volume is lower. Okay. And then so they only talk about these two. Okay, I'm gonna go with the flow. Then they talk about Charles' law. Charles' law, they give you the summary in terms of volume, right? Charles' law, volume relates to temperature, directly proportional. Bohr's law, volume relates to pressure. Then they combine these two. Okay, when they combine these two, we then get what is called the combined gas laws. So I really don't recall if you had one on number of moles. So I want to go ahead and cover that real quick before I continue this part here. The Avogadro's law. Because I could have sworn you guys had Avogadro's law, but somehow it's not in this new slides. So Avogadro's law, just in case, this one relates volume. So remember we had the P, V, T, and N. I forgot the N. That's okay. P, V, T, and N. In Avogadro's law, we relate the volume to number of moles, keeping pressure and temperature constant. So essentially the rule says the volume of the gas, the rule is the law, is directly proportional to the number of moles. Okay? Directly proportional. If pressure and temperature are left constant, temperature are constant. So we saw this before, right? Volume is proportional to number of moles and vice versa if pressure, temperature is constant. So just like we did before, replace the proportionality sign with the equal sign. Volume equal constant and divide both sides by n. So we get volume 1 over number of moles 1 equal volume 2 over number of moles 2. And if you encounter a problem like this is how you will work it out. you will use this equation provided here. I'm just giving you the tools required. Now, since they didn't really cover this law, we won't have questions in this case here, but your homework may have these questions. Okay? And then from here, I'm going to combine all the three laws. In combining the three laws, I'm going to write the statement and then I'm going to show you guys the equation. So the combined gas laws. The volume of a gas is directly, ooh, I can't spell anymore, directly proportional, I think my ability to spell just went out the door, proportional, there it is, and to temperature, and inversely proportional to pressure while moles are constant. So from this statement here, which you may or you may never use, and I'm just preparing you guys for whatever is out there, we get P1 V1 over T1 equal P2 V2 over T2. Sometimes the N is right here, N1, and then we have N2. So when I was in school and I had to memorize this, because we had to memorize this, we didn't have access to our notes. We just memorized this law here, and then we got the other laws from this law. So let me show you how you can do it. I'm going to highlight this. If you look at the top parts here, the yellow, and the yellow essentially gives you, I'll highlight this here, the yellow part gives you Boyle's law equation. And then we have who? Charles' law. I'll make him green. Charles' law shows you this relationship here. And so this is going to be Charles' law. Charles' law relates the green parts to each other, right? V1 over T1 equal V2 over T2. And then who else did I show you? Avogadro. Because there are more laws here. I'm always trying to stick to the number that you guys cover. Oops, no, last one. What color do I want for my highlight? Blue? They don't have a pretty blue. No, that's really important. Ooh, I'll go with that one. This last one here, Avogadro's law. It's this diagonal relationship right here. Okay, that will be Avogadro's law. So from this combined gas law, you can get all these different laws, and you can see how they're in there. It's like a combo meal that contains a lot of different things. This is a combo equation that contains a lot of different laws inside, all in one, right? And so they're showing you here, and then everything on the left will be the first condition, everything on the right will be the second condition. So you can get, Boyle's law from there, Charles' law, Avogadro's law. There's another law called Pressure's law, and that's all in here, all together in the combined gas law. So the one they show you here doesn't have the number of moles, but I show you the one with the moles just in case. And this is called the combined gas laws. Oh, okay, I'm looking at the time here. So what I'm going to do when we meet next time on Thursday, Okay, so I'm just thinking about the chapters that's left over, and you guys have 3 chapters before your next exam, right? We won't be able to cover all of them in just one day. We won't be able to cover 2 chapters in one day. Can anybody meet tomorrow?
Yeah.
Okay, same time, because I'm sorry. I mean, I will record it, and then post it. So if you can't come, that's okay. But I'm realizing this is a short semester. So even though I said 2 days, we're not gonna finish all 3 chapters in 2 days. It's taking me almost 2 hours to finish this chapter here. Yeah. So if I can have at least one person, it makes it easier, you know, for me to go through it faster and to be dedicated. So tomorrow I'll do chapter 4, and then I'll get as far as I can, and then chapter 5 will be done on Thursday. That way we can finish all this, and then you guys can have more time over this before you do your exam number 2. That covers 3 different chapters. By the way, yeah, your second exam covers 3 different chapters. Yeah. So yeah, I'm almost done with this chapter over here. I will have a couple of questions tomorrow to add to this, but this question here just shows you how to combine all the gas laws in the problem. And since I hadn't memorized this when I was in school, I had to memorize a lot of things. I'm not good at memorizing. I just applied the gas laws to the combined gas laws to almost every question out there. So a cylinder in an automobile engine has a volume of, so the volume given to us is 352 centimeter cube. The engine takes in air at 25, so temperature 1 is 25 degrees Celsius, and the pressure of 0.945 atmospheres. The pressure 0.945 atmosphere. The compression stroke squeezes, okay, I have no idea. I'm assuming this is a part in a car. Squeezes and heats this gas until the pressure is, so we have a second pressure here. I'll call this P2, 4.95 atmosphere, right? And then the temperature 2 is 95 degrees Celsius. What is V2? What is the final volume of the cylinder? So we got CMQ, right? So I'm trying to make sure that my pressure unit doesn't change. So I'm comparing ATM with ATM, check. Degree Celsius with degree Celsius, check. That means CMQ with CMQ, check. Okay. My formula is P1V1 over T1 equal P2V2 over T2. Even if I chose to use the one with the N here and 1 and N2 here, they never mention anything about the number of moles changing. So N1 equal N2. So this pretty much cancels out. It drops off because they match, right? So we're left with P1V1 over T1 equal P2 times V2 over T2. Okay, I'm trying to figure out what are we trying to solve for again? Oh, V2. So I'm going to try to get it by itself, okay, in the rearrangement here. Mathematically, we want V2 by itself. To get V2 by itself, we're going to multiply this by the inverse of everything else that's not V2. What do I mean by that? I'll just take T2 and write it on top, and then P2 on the bottom, and multiply the left side by the same ratio, T2 over P2. So T2 and T2 cancel out. P2 and P2 cancel out. If I multiply expressions by the inverse of what I have, I can get to cancel it out. So this is gone, this is gone, this is gone, and this is gone. And now I have V2 by itself. On the left side, I have T2 times P1 times V1 over P2 times T1. I'm not done. Now that I have everything isolated, V2 is by itself. I have to go back and remember, with temperatures, you have to use Kelvin. So I'm going to add 273 to get it in Kelvin form. Temperature here is 25 plus 273. I have 298 Kelvin to the left. To the right, I have 95 plus 273. That's how we convert to Kelvin. I have 368 on the right. So this is what I'm going to be using. Okay, I hope I can remember this in order. 352 V1. Oh, it's not in order. Okay, T2, where's my T2? 368. 368, that's Kelvin, times my P1, what's P1? 0.948 or 0.945 ATM. It was 0.945, right? Let me verify that. Yep, 0.945 times, what's my V1? Go back here. 352, 352 centimeter cube. Ooh, this M is really just going on and on. Okay, centimeter cube. And then let's see, P2. P2 should be on the right. Yeah, 4.95. 4.95 ATM. Then I had T2, no, need T1. T1, 358. 358 Kelvin. Okay, I finally got everything, right? K and K cancel out. ATM and ATM cancel out. My answer would be in centimeter cube. That would be my V2. So I'm going to plug this and work it out. 368 times 0.945 times 352 divided by 4.95 divided again by 3558. So my calculator, I'm inputting like this: 368 times 0.945 times 352 divided by 4.95 divide again by 358. So your calculator can understand what you mean. I get 69.1 centimeter cube for my volume, for my V2. Let me see what they get. They work it out, they rearrange it. How they get a very different number from me? Okay, let me see. Let me make sure. 368 was T2, right? 368. P1 was 0.95. And then what is this? This is V1, 352. And then P2 is 4.95. Was P2 4.95 from up here? Yeah. And then trying to see why numbers are so different. 4.95, and then I got here 358. Their numbers are okay. Let me try this again, because I don't even see a 368 here. Oh, they didn't work it out. Okay, let me see. Let me try it again. 368 times 0.945 times 352 divided by 4.95 divided by 358. Get the same number. Let me make sure I copy the right numbers up here. So this is 298 for my. Oh, one of my temperatures is wrong. T1 is wrong. It's supposed to be 298. What did I write? T1 is supposed to be on the bottom. This is supposed to be 298. 298. That's the issue, right? T1 is 298. And then T2 is 368. I got that one. And then V1 is 352. I got that. Where did I get the 358 from? Okay, so that was my issue. So this should be, this bottom number here should be 298. So let me see. 368 times 0.945 times 352 divided by 4.95 divided by 298. Finally, okay. Yeah. So finally, my answer is a lot closer to their number. And it has to do with the way they rounded things up. So I get 83 centimeter cube, which is a lot closer to what they have. Okay. So at some point they were using 273.15. At some point they weren't, but the difference has to do with that, how you convert the temperature from degrees Celsius to Kelvin. So yeah. Oh, how is my answer so different from theirs? My goodness. And or I think we're all tired because I didn't say anything. The temperature is supposed to be what 21 degrees Celsius, and I wrote 25, and then we got this number. Yeah. So the method is correct. Here's the thing: the method is correct. The answers are slightly off because it is getting to the time of the day. It is after 6. We are all fatigued. But yeah, so that's why my answer is slightly off. 8. So that's where 294 right here. Yeah, it's supposed to be 294. So once you work that out, you get 84, which is what we get, 84 centimeter cubes. So this is supposed to be 294. Yep, and this should be the last major one. Beyond here, it's talking about converting to SCP. I'm not gonna do much with this part here. What I'm gonna do here, which is obvious, we've gone long enough, is they do talk about Luzak's law for this last part. You guys haven't done this last question, have you? You're not done anything with SCP just yet, so you haven't done the homework, so it's hard to really tell. Well, let me at least go through this last 2 slides so I can know that I'm done with it, because I don't really have a lot of time tomorrow or the day after to complete this. Tomorrow, I will try to go over homework problems, a couple of them, just to make sure we're on the same page. And then we'll dive right into chapter 5. And then on Thursday, we'll do chapter 6, which will take me a little bit long, but yeah, we'll get that done. So let's work on this part here. This question is saying the volume of a sample of nitrogen gas is measured as 3.6 liters. They give you the pressure, the volume, and the temperature. What is the STP volume of nitrogen gas? So I want to define STP in the context, right? So in this one here, I'm going to add a page so I can write on that. We are provided with the volume as 3.62 liters. This is the volume. We're provided with pressure as 0.843 bars. That's this right here. We're provided with temperature as 16 degrees Celsius. And these are all the initial conditions. So V1, P1, T1. Then we're being asked at STP. In this chapter here, STP, standard temperature pressure, STP. S stands for standard temperature, and then P stands for pressure. Okay. Standard temperature is 0 degrees Celsius. The pressure is usually 1 atmosphere. So within this question here is understood the temperature is 1 atmosphere, and then the pressure is going to be so the temperature is the pressure is 1 atmosphere, the temperature is 0 degrees Celsius, right? So once you have all this, they're asking you what is the volume. If you have 0 degrees Celsius and the pressure of 1 atmosphere, what is your volume? So the volume will have to be in liters. So when I look at these units right here, these units do not match. We have to convert our units to atmosphere in order for everything to work out, right? So in the previous slide here, they define what the pressure conditions are, what the temperature conditions are. Now, I was noticing this is why I'm getting distracted. They define the pressure conditions to be 0 degrees Celsius, which is correct, and they define the pressure here to be 1 bar. We normally define it as 1 atmosphere, so this works here, 1 atmosphere, or we can use just 1 bar. So based on this question, to be consistent with that, we're going to be using this one here because this is how it was defined. Okay, we're going to be doing P1 V1 over T1 is equal to P2 V2 over T2. V1 is given to us right here, is in the right unit. Pressure here, they had bar. We'll leave the units as is since it was defined that way in the question. The pressure is bar. P1, we have the units. Temperature has to be converted to Kelvin. We'll add 273 here plus 273. Let me make sure I have the right number, 16 plus 273. We end up with 289, right, Kelvin? Our second temperature is 0 degrees Celsius. We'll add 273 Kelvin here. So looking, we're trying to find V2 just like before. Multiply both sides by T2 over P2. This cancels out. Multiply this side by T2 over P2. And we end up with, just like before, T2 times P1 V1 over P2 T1. Since you guys have access to your notes, just go ahead and highlight what's important, what we are working on right here. Just highlight this part. This is the equation you need. Okay? We're going to be using this to solve for V2. I think the yellow one is a lot brighter. Yeah. We're going to be solving for V2 using this equation right here. So I want to work it out. T2, I have my T2 right here. T2 was essentially 273 Kelvin. My P2, according to the definition in the previous slide, was equal to 1 bar. And these together make STP. So I have to consider that when I'm plugging these into the equation. I have my T2 right here. It's going to be 273 Kelvin. This is done. I need P1. P1 is written right here as 0.843 bar. I just use that. I need V1. Where's V1? Times 3.62 liters. I just use that. Divide this by P2. P2 they said was 1 bar times, where's T1? Right here. 289 Kelvin. 289 Kelvin. Okay. So over here we have 273 times 0.843 times 3.62 divided by 1 divided by 289. So it shows here 2.88, and the unit for the volume was it liters? Yeah, the volume was in liters. So we have our final answer is 2.88 liters, and the unit is liters for our volume 2. That's what they get also. Ooh, wrong thing. Highlighter right here. Okay? So this is just us practicing how to use the equation provided to us. And they're showing us more relationships here between Amonton's law and Gay-Lussac's law. We can use the relationship we had before to see this relationship here. I'm not sure if you guys have homework questions that has that relationship, but just in case, somehow it just abruptly ends right here. But just in case you need this relationship here, P1 over T1 equal P2 over T2, and this will help you solve problems. And this is only true when number of moles are kept constant and the volume is kept constant. So this is all I have for today. It's already past 6. Tomorrow, what I'm going to do is look at some of your homework problems, and then we'll try to solve some of the, just to see what is in your homework. Because the questions keep changing, and I don't get to keep up with it. So I want to make sure what we're covering in lecture is consistent with what's covered in your homework. Do you all have any questions?
No, but
Okay.
it's a lot of equations.
Okay. I know, right? And it gets, the information gets heavier when we get to chapter 5. That's why I need more time. I need a whole lecture period for chapter 5. So I'm going to hit the highlights tomorrow. And then if I can, I will start with chapter 5 tomorrow to give you guys more time to, to kind of spread it out. Chapter 5 is a lot of information also. So, but yeah, go sleep on it. You have between now until your next exam. All right. Okay. Well, I'll see you guys tomorrow at 4. If I happen to forget, please send me a reminder because this is not my normal time. I'm just trying to help you guys before your next exam. But okay. Well, you guys have a nice evening. Get some rest, and then go ahead and review this after you've rested. Okay. Bye.
Bye.
Okay. How do I exit out of here? Oh, let me stop sharing.